Welcome to the Geography 215 Chapter 3 math video. The learning objectives for this math video are to learn a little bit about radiation, to learn about the Stefan-Boltzmann's law, to learn about the inverse square law, to learn about solar radiation transmission, and to learn about albedo. Let's start with radiation. The Earth and the Sun have different emission rates. What you're going to want to do, and to learn more about the emissions, read about the radiation laws in Chapter 3, starting on page 93 in your textbook. This page in your textbook will talk about different types of black bodies and other types of systems. Getting into the Stefan-Boltzmann's law, the Stefan-Boltzmann law is E equals Stefan-Boltzmann constant times absolute temperature to the fourth power, where E is the total energy flux emitted by a black body across all wavelengths. Taking the Stefan-Boltzmann's law into account, what happens when the temperature changes? Keep in mind that the temperature is to the fourth power. Using this information, say the temperature changes 2, so T equals 2. Once you plug in 2 to the fourth is 16. So your new equation would be E equals the constant times 16. Therefore, a change in 2 of temperature would result in more of a change in E because instead of 2 times, it would be 16 times due to the fourth power. Let's move on to the inverse square law. According to this inverse square law, doubling the distance traversed by radiation reduces its intensity to 1/2 squared, or 1/4 of its initial value. That is, in terms of proportionality, E equals 1 over r squared. Let's try a problem. As radiation travels from the sun outward into space in all directions, the intensity of the radiation, or energy per unit time per unit area, diminishes as the inverse square of the distance traveled, such as the inverse square law. If Earth's distance from the sun were 4 times its present value, the intensity of solar radiation reaching the planet would be what of its present value? First, take the inverse square law equation, which is E equals 1 over r squared. The question asks what happens if the Earth was 4 times away from its present position. The intensity of solar radiation reaching the planet would be what its present value? The main variable you're going to want to look at before you plug into the equation is what if Earth was 4 times away from its present position? Keyword 4. Therefore, with your equation, E equals 1 over r squared, r will equal 4, because it asks about 4 times away. So insert a 4 in for r. So your equation is going to be E equals 1 over 4 squared. E equals 1 over 4 squared is 1/16. Going back to the question asks what happens if Earth was 4 times away from its present position. The intensity of solar radiation reaching the planet would be 1/16 its present value. Let's move on to solar radiation transmission. Consider what happens to a solar beam traveling through the atmosphere on some particular day. Within the atmosphere, 35% of the radiation is absorbed and 15% is scattered or reflected to space, mostly by clouds. Keep in mind these values can change, so read the question carefully. What percentage of the solar radiation incident at the top of the atmosphere is transmitted to Earth's surface? So for this question, 35% of the radiation is absorbed and 15% is scattered or reflected to space, mostly by clouds. Keep in mind, again, maybe in future questions, that these percentages can change. But for this question, It's 35% and 15%. So the beam coming from the sun is at 100% before it is scattered or absorbed. Take the scattered and absorbed values. So again, 35% of the radiation is absorbed, and 15% is scattered or reflected to space, mostly by clouds. So we're going to want to subtract the absorbed and scattered from 100%, because that's what's getting taken away from the beam that's going to eventually make it to Earth. So the transmission to the Earth's surface is 100% minus 35%, which is absorbed, and minus 15 more percent, which was scattered. So 100% minus 35% minus 15% equals 50%. So in answering the question, consider what happens to a solar beam traveling through the atmosphere on some particular day. Within the atmosphere, 35% of the radiation is absorbed and 15% is scattered or reflected to space, mostly by clouds. What percentage of the solar radiation incident at the top of the atmosphere is transmitted to Earth's surface? The answer would be 50% in this case. Let's move on to albedo. Lighter objects have a higher albedo, and darker objects have a lower albedo. Basically, albedo is how much is being reflected. As you can see by the figure on the slide, the white object reflects more, so it has a higher albedo. You can see 100% coming in, but 80% going back. The darker object absorbs more, so with 100% going in, 10% is leaving, so it has a lower albedo. So, for example, snow cover would have a high albedo because it's white. A dark roof on a house would have a lower albedo because it's dark and it absorbs more and reflects less. So think about ice, for example. Ice would have a high albedo, but if it starts to melt, it would get darker, so it would have a lower albedo. This ends the Chapter 3 math video. As always, please let me know if you have any questions.